All right, we're going to go over all 4 questions and what my expectations are for them. But first, there's a simple truth here I'm hoping you're recognizing. So far in our discussion, we've really only had 3 things as it comes to formulas: the definition of work, the definition of kinetic energy, the work energy theorem, and although we've talked about some other stuff like graphing and springs and such, these are the only things necessary for this problem. So let's talk about question number 1. The amount of work done as the ball goes from where it started to 45 meters above where it started. To calculate the amount of work, we're looking at this. This will be the work done by an individual force. Can you think of a force that is acting on the ball as it's been fired upwards? So I can see only that gravity is acting on the ball as it moves upwards. There are 3 things I need to know about the work done on the ball. First, I need what force is acting on it. If you say gravity, that makes this 20 newtons. There's 20 newtons of force acting on the ball. That's the weight of the ball. It rises 45 meters into the air. That's its displacement. Let's see. The angle here, though, you need to be careful. We use theta for everything. You have to understand that this is the angle between the displacement and the force. Every theta on that equation sheet can stand for something different. In your notes, I would not leave any formula with just theta in it without a simple explanation as to what that theta is about. Or, be at your own risk here. The ball moves with a displacement that is upwards, but the force acting on it is downwards. This is the weight. What's this angle? 180 degrees. So this looks like negative 900 joules. So that's how much work was done by gravity on the ball. Any question about that? All right. Are there any other forces doing work on the ball? Can you think of it? Is there anything in contact with the ball? String, surface? So none of the contact forces. Is there friction acting on the ball? It's not sliding against the surface. And I specifically said to neglect air resistance. So this is the only thing that does work on the ball. So this is also the answer to number 3. That has to be the total work on the ball. And the total work is equal to the change in kinetic energy on the ball. So all of that is negative 900. Now here's the thing. You're asked to figure out how much kinetic energy the ball had at the bottom. I'm adding that question, and I didn't ask first period to do that, but I'm asking you guys to do it because it came up in first period, a problem. So this part's just calculating kinetic energy, which is just kind of a plug and chug activity. I don't know how much this is, 35 squared. Do any of you know what it is? You didn't do number 2. I'm sorry, what? Okay. If you're trying to learn what's happening here, and I really hope that you are, then one of the things that you should be asking yourself, first, does the ball have enough energy that it can lose 900 joules? The reason this is an important question is this is by how much the energy of the ball changed. If I was trying to trick you, I would give the ball less energy. Say, what if I told you the ball is only fired at 20 meters per second? How much energy would it have now? 400 joules. Would it have 900 joules that it could lose? The energy of an object can't be negative. It's going to take 900 joules for the ball to go from where it started to a place 45 meters above where it started. That's how much energy it's going to take. The ball has to have that energy in order to arrive there. If I was going to try and trick you on the test, then I would make sure the ball didn't have enough energy to see if you would know what that means. So you need to know what that means. That this represents how much the energy changed. The object has to have enough energy in order for it to lose that much energy. If it doesn't, it can't change by that much. The most the ball could lose is 400 if it was shot at 20 meters per second. So I need you to be more than able to just deal with these. You have to be able to think about what it is you're doing. The numbers aren't enough. On the other hand, we have enough information now to figure out how fast the ball is going at the top. That's another kind of plug and chug activity. It's not particularly interesting to me, but it is using all of the things together. It's this. The ball started with this much energy. It lost this much energy. I can figure out now how much energy is left with the ball because it's K final minus K initial equals the total work. So if I'd like to figure out how much kinetic energy it has at the end, that's probably going to do it right there. That suggests that the final is what, 325 joules? My subtraction works. Now that's not the answer to the question. The question was how fast is it going? But if you know the kinetic energy, it's likely you can figure out how fast it's going. So 1/2 mv final squared is equal to 325. And correct me if I'm wrong, is that 18? I'm pretty sure. But check. It's like 18.09, I think. I'll wait patiently. So, not terrible, but maybe another practice. Maybe another practice. So let's try another practice. I'll continue to provide a little bit more practice. This one, I'm going to switch it up on you from something we talked about yesterday, just to see if you can kind of roll with it. Really similar question. I just changed by a little bit. I have a toy car. It's on a level surface. It's traveling at 3 meters per second. It's going to experience a force as displayed in the graph. So I give you a graph of force versus displacement. The car experiences the force over the entire displacement of 9 meters. I'd like to know how much total work was done on the car, by how much its kinetic energy changed, and how fast it's going now. Same kinds of questions as before. I'm just providing you with a different kind of information in dealing with how the car had work done. Let's see if you can roll with what we talked about yesterday. So give this one a try. Talk to people around you. I'm hoping you'll be more successful. I'm really only interested in the last answer. So, but you have to do the intermediate ones to kind of get there. It appears as though many folks are capable of working this through, and that makes me happy. So let's just make sure we have consistency here. This problem, you can't figure out the work done using the formula work equals force times distance times the cosine of the angle, this will not work. And the reason is because the force is changing over a portion of its motion. If the force was constant over the whole motion, it'd be fine, but because it's changing, you have to use the graph. Now, because of that, you just got to find the area of the graph. And it looks like most everybody was able to find that it was 70 joules of work as put by the graph. Now, I don't want to be complacent here. That is the answer to number one, but it's only the answer if that's the only force doing work. There are other forces acting on the toy car. Gravity's acting on the toy car, normal force acting on the toy car. Because it's rolling, there's probably not any friction acting on the toy car, not in a meaningful way. So you should evaluate all of the forces. This is just one of them. But there's nothing else that appears to be doing work on the car. It'd have to have a component of the force in the direction of motion. Nothing here seems to have that. So this would be the total work. And because it's the total work, it's also the change in kinetic energy. So I think we're back. Go ahead. It's trapezoid. So I did some of the bases times the height. So I got 5 plus 9 times 1/2 times the height of 10. Now you could have broken it up into a triangle and a rectangle if you wanted. It would have been 10 times 5 and then 1/2 times 4 times 10. But I did it as a trapezoid. Mm-hmm. Now, the last part of this is simply recognizing that we have the change in kinetic energy, but in order to figure out how fast it's going, we have to understand that this object already had some kinetic energy. So although it changes by 70 joules, that's the difference from where it started to where it is now. The car already had some kinetic energy, so I need to figure out how much kinetic energy it started with. That's going to be 1/2 mv squared, so 1/2 times 3 times 3 squared. This will tell me how much kinetic energy the object started with. And then I can use that to figure out how much kinetic energy it has after it's experienced the force. So, and to be quite honest, I don't remember how much total kinetic energy it has now. 3 squared is 9 times 3 is 27, and half of 27 is going to be 18 and a half. 13 point, not even close. 13 and a half. So this has got to be 83.5. Now, that's not the answer. That's just how much kinetic energy it has after experiencing the work from the force. So if I want to figure out how fast it's going, that's 1/2 times 3 times the final velocity squared. That'll give me the final answer there. So do a little bit of arithmetic, and that's how you get the 7.5 meters per second. I've not given you any practice. I thought I had, but I had not. So I'm going to post your homework assignment tonight. It is not due tomorrow. That would just be cruel. But I'm going to not circle, but I'm going to star 3 of them and say that you should do those tonight in preparation for your test tomorrow, your quiz tomorrow. We're going to have a quiz like this tomorrow. It'll be that fast, about 10 minutes. My expectation is it won't be terribly difficult, but take a look at the questions that I've highlighted for you in preparation for tomorrow. The actual homework will be due after we come back from the break, probably Tuesday. I won't make it due on the Monday. Yep.
So there's not going to be like any written response? I don't know. I thought you said FRQ this Friday.
This is like an FRQ. Yeah. So there'll be a written response. Well, I mean, it's a calculation. I'm sorry. I'm not trying to deceive you. You've done what the quiz is going to look like tomorrow. There might be something that we talk about today added to it, but not much. So let's talk about more today. I don't want to end here. So we talked about springs before. Anything that's elastic is going to have the properties of a spring. So things that are springy basically attempt to return back to their original shape. I said we were talking about this a little bit yesterday. The problem is that a spring provides a non-uniform force. So we can't use the definition of work that we've come to use so far in this unit, because the definition of work that we have is based on a constant force. So if I want to know the work done when I compress a spring, I'm not going to be able to use our standard information here. I tried to convey that you could use a graph to figure it out, but I'm not trying to be attached to that. If a ball is rolling towards the spring and it has some kinetic energy, would you agree that it's likely the spring is going to stop the ball? But in stopping the ball, it's going to cause the spring to be compressed. So there'll be a moment where the ball is stopped, pressed up against the spring. Now, it's likely the spring will return back to its original shape and push the ball back away. I don't think any of you who have ever seen a cartoon has not seen something like that before. But understand that there will be this moment where the spring is fully compressed and the ball has come to rest. A state that's going to look like, this, where the spring is going to be all compressed up and the ball for a fraction of a moment is going to be just stopped. The ball had kinetic energy, and for the ball to be stopped means that something had to change the ball's energy. Now, I'm not trying to make this, a huge reveal. The energy the ball had went into the spring. The spring did work on the ball, which means the ball did work on the spring. So now the spring has energy. We calculate that energy in a very specific way. Work done on or by a spring. I'm putting on or by because it really depends on what we're talking about. The work done by the spring on the ball is going to be equivalent to the work done on the ball by the spring. So how much is that? It's equal to 1/2 kx squared. Now, each part of that has something important to deal with, but let's first begin by kind of understanding what these pieces are. The value k here is something we talked about a couple weeks ago, but I want to bring it back up. It is the spring constant. If you're reading a problem, its units will be newtons per meter. That's how you can tell you've been given the spring constant. Now, a few things about spring constants that I think are important. Spring constants are big numbers. So 5 is not a big number. They're going to be hundreds or thousands. I want you to think for just a moment what the spring constant tells you. It's how many newtons it takes to compress a spring an entire meter. There are 4 springs on your car. When you sit down in your car, how far down does your car sink? I mean, a couple inches. Your car sinks a couple inches. I don't know that mine is got old loose springs, and mine only sinks about this much when I sit in the car. I would say your car probably does not sink very much. You are several hundred newtons. When you sit in your car, if it doesn't compress very much, that means that it can take a lot of force and not change very much. So spring constants are big numbers. They can take a lot of force without changing very much. I don't have any spring that can actually be compressed or stretched an entire meter before it would bend. A meter is a long thing. So spring constants tend to be big numbers. The springs don't move very much. Maybe a couple of centimeters is how much springs change their size. So we generally think of the spring constant as being a big number. So if you do a problem, if your spring constant comes out to be like 0.4, you've probably made a mistake. I would expect it to be hundreds or thousands. Even for toys, they're not very big. You figure toy guns that shoot like little, ping pong balls, you've seen those kind of things, they still have a spring constant that's in the hundreds because they only compress about this much and they shoot the ball a couple meters per second. So you have to expect that spring constant is going to be a relatively big number. X, though, it represents the compression or elongation stretch of the spring. And this also works if you stretch a spring, you store energy in it, or if you compress a spring, you store energy in it. So if I'm talking about like a bow or bow and arrow, I'd be talking about more like elongating the spring. But if I'm talking about like a spring launcher like this, then I'm talking about compressing the spring. So that's what these values mean. You work this out, it will come out to be in joules. So this is a form of energy. Now, there are a couple things about springs I'm leaving out. One of the things is the spring always has to have something that's holding it in place. The only way a spring compresses or gets stretched out is if something actually doesn't move, like the wall or something. So springs require this interaction with a surface. We're going to talk about what this interaction is about when we come back from the break, but be aware that there has to be something that attaches to the spring. A spring just sitting there on the ground doesn't have any way to apply a force unless something holds one end of it from moving. Also, we are currently talking about ideal springs. Real springs, well, they do other things. Real springs have limits. If you pull too hard on a spring, you'll bend it. If you push too hard on a ball, you'll pop it. If you pull too hard on a rubber band, it'll snap. I mean, they have limits, elastic limits or physical limits. And if you go too far, they no longer obey the rules. They'll break. Or if you push too hard on a spring, the coils will all start touching each other and they can't compress anymore. So ideal springs can be compressed as far as you need them or pulled out as far as you need them. And they always work exactly the same and they always return to their original shape. But real stuff doesn't. Real stuff wears out. Rubber bands get hot and after a while don't work as well. Stuff like that. So they will probably ask in future questions about the difference between ideal and real. I'm not going to tomorrow. All of our stuff is going to be ideal for the time being. So what I'd like to do is I'd like to work out kind of a sample question of how a spring might be used in a problem. And we're going to start with one that's relatively easy just to kind of ease us into that. We are kind of looking at what I want you to do right now as a problem goes. So let's assume that we have a spring with a spring constant of 200 newtons per meter. And we have a 2 kilogram ball rolling at 4 meters per second. And it's rolling towards the spring. I'd like to know how far the spring compresses when stopping the ball. Okay, does everybody hear the question okay? I'm not going to write it down, but I'll say it again. I'd like to know how far the spring compresses while stopping the ball. And we're going to step through this problem together. First, can we agree that there's not much different when it comes to what's happening to the ball? That it's having a change in kinetic energy. And we can figure out the total work required by looking at the change in kinetic energy. We can't figure it out by calculating the work on the spring because we don't know how far the spring is compressing. So without that, we have to find a different way to calculate the total work. But we have the initial speed of the ball and we have the final speed of the ball. So we have information about its kinetic energy that we can use in finding out the total work done on the ball. I'm saying this because there's more than one way to calculate total work. And I want to make sure that you're not getting complacent. You can calculate it by calculating the change in kinetic energy. That's one of the ways you can calculate total work. So don't always think it's about a force. It's not. But this one's easy, though. It's going to be 1/2 times m times v final. And I'm going to subtract 1/2 times m times v initial. The change in kinetic energy. I expect it to be negative. I expect that because the ball is being stopped by the spring. So we work this out and we get that it's, I think, negative 16 joules. All right, 4 squared is 16. Half of 2 is 1. 1 times 16 is 16. It's negative. The ball lost this energy. This is the total work done on the ball. Now, there are a variety of forces acting on the ball. Gravity, normal force. You any of those do work on the ball? You need to evaluate that. Gravity is acting downwards. Can it be doing work on the ball? Only if it's moving up or down. Is the ball moving up or down? No. There's no component of gravity in the direction the ball is moving. So it's not doing work on the ball. Is the normal force doing work on the ball? No. If the surface is level, there's no component of the normal force in the direction of motion. It's not doing work on the ball. It's rolling, so friction is not really a factor of this problem. The only thing I think that does work on the ball is the spring. Here's where you have to be careful. And I want to just be clear. The spring has to take away 16 joules of energy. It's negative because it has to take that energy away from the ball. But when I use this expression for the work done on the ball, the work is negative on the ball, but positive on the spring. The spring is gaining this energy at the expense of the ball losing it. Remember, the negative sign here is about where the energy is going. So I want you to be kind of not concerned about what I'm about to do. I'm just going to say that the spring has to have 16 joules of energy in it in order to stop the ball. I'm not worrying about the negative sign. I'm trying to remember the negative sign means the ball lost that energy for the spring to gain it. That's why I put on or by the ball here. Or I'm sorry, on or by the spring. To make sure we understand that the spring is taking the energy away from the ball and storing it in the spring. So 1/2 times 200 times x squared equals 16. This will require your calculator skills. It's like the square root of 4/25 or something. It's a small number. Sounds about right to me. It's going to be a small number. It's a toy, but it's still 0.4. I mean, it's still that far. It'd be a pretty big spring for the ball to have to roll into. So just keep in mind that I expect the number to be small, but I mean, if I was actually making this, I would probably need a stronger spring than that to stop this ball because that's too far for it to go. Practice tonight. Quiz first thing tomorrow.